Alright, what's up guys? I'm Matt, back for another of Matt's math tutorials. Today we have a problem from a math competition that I did recently. I'm not sure about legally if they own this problem, so I can't show it in this video, but I just figured, jail can't be that bad. So Uncle Jack is 17 years older than his nephew Kelly. If you create a 4-digit number with Kelly's age written before Jack's age, the result is a 4-digit number that is a perfect square. 13 years from now, the same statement would be true. Find Kelly's present age. For example, if Kelly was 36 and Jack was 53, the 4-digit number would be 3653, 3653. That number is not a perfect square, so those are not the correct ages. All right, so I immediately see Uncle Jack, Kelly, so I'm going to write Jack's age as J and Kelly's age as K, just because variables are nice and these obviously represent the first letter of their names. So if Jack is 17 years older, then we actually know that we can set them equal to each other if we add 17 years to Kelly's age, right? Because Kelly's age plus 17 years is going to be Jack's age, right? He's 17 years older. So we have that. Now, if you create a 4-digit number with Kelly's, so they're talking about like, if they had the 36, they had the 53, and they just brought them together. That's not a subtraction sign. That's just like they brought them together to make 3653. Now, I don't think we really have like a math thing to handle that, but something useful you can do. Look, if you have, right, this 36, if that was by itself, we couldn't just add it. But if we had, say, 2 zeros, then we could just add the 53, right? So actually what you can do is you can multiply this age by 100, right? So 36, or this is all just the example they gave us. This isn't any numbers that we're actually going to use, but 36 times 100 plus 53 equals, of course, 3,653. So this method right here, the multiplying by this power of 10, actually gives us a way to kind of shift it over, right? Even though normally that's not really, there's no operation for that really. So it seems like in this situation, we have j times 100 and then plus, oh, actually, no, it would be Kelly's age is actually going first, right? Yeah, so actually it'd be k times 100 plus j, right? And this equals, it's just some 4-digit number and it's going to be a perfect square. So let's just call that, we know it's a perfect square, so let's call it like x squared, right? Because we know it's perfect square, so that might be a useful property to just have in the notation, right? So now 13 years from now, the same statement would be true. So 13 years, that's the equivalent of just adding 13 to both ages, right? So let's try k plus 13 times 100 plus j plus 13, right? That's also going to be a perfect square, but it's not going to be the same perfect square. So let's call this y squared. All right. So now we have these two expressions, right? But we already have j in terms of k, right? Because we want to kind of get rid of variable here. There's 4 variables in these two equations, right? So it's not really going to work out well. So we want to get rid of one of them, and we see that we have j equals k plus 17. So we can do a pretty simple substitution, right? To get, move this over just a little bit more, to get uh, k times 100 plus, and instead of writing j, we're going to write what j equals, which we already know is k plus 17, right? And that equals x squared. And now, same thing down here, k plus 13 times 100. That part doesn't change, right? But this part does. So this is going to be, instead of j, it's going to be k plus 17. 17, right? And then it's going to be plus that 13 still, right? That 13 is still going to be there. And that equals, I really don't need this stuff right here, whatever. That equals y squared. Okay, so now let's combine some like terms here, right? So here we have 100k plus k, that seems like 101k, right? Because this k is basically a 1k and then plus 17. And then here we have This is a bit more complicated. 100k plus 100 times 13 is, of course, 1,300, and then plus k, and then let's just combine these, right? That'd be 20 plus 7 plus 3, right? Obviously, that's 30. And then we have same thing, 101k plus 1330. Is that right? Okay, I think so. All right. So let's make sure I'm doing this right. Okay, before Jack stage. All right. So it should be right. So now we know that these are both perfect squares, right? So there's a useful property of perfect squares where you can do a square minus another square, right? So let's do that. Let's do y squared minus x squared because, well, a squared minus b squared equals um, a plus b, a minus b. Now this shouldn't be a surprise, right, to anybody. Oh, wow, I don't know what just happened there. Okay, so this should be familiar, right? It's pretty useful. And I don't know if there's really a reason to do it right here, but we have two squares, right? And it seems like if we subtract them, maybe some like terms will cancel out, right? So it could be a good thing to do here. So let's do this y squared, right? 101k, that's k, plus 1330, right? And that's the y squared, minus, and then let's do this whole thing, right? The 101k plus 17. And that's the same as saying y squared minus x squared, right? And so we combine these, we see this looks like it's going to cancel out, right? Which is pretty useful because that's a whole nother variable gone, right? And usually in a problem like this with a lot of variables, you want to kind of reduce the variable count if you can at all. So that's going to be 0k, so let's just ignore that, I guess, then. And then this 1330 minus that 17, that'll be 1313, okay? And so we're left with just 1313 on this side, which is very helpful, equals y squared minus x squared. Okay, just pretend those are both 2's. So now we can use this, like I said, right? This a plus b, a minus b, conjugate pair, I think it's called. Basically, you're kind of just making 2 factors, right? And so that'll be y plus x and y minus x. Okay, so this, full disclosure, when I was doing the problem originally, this is pretty much as far as I got. And then I kind of hit a wall because I didn't really know what to do here. I mean, we're trying to find k, right? Our goal is this value right here because this is Kelly's present age, right? Kelly's present age, k, that's what we're trying to find. But now we're kind of in this different realm of y's and x's. And even if we find this, we'd have to square it and then get our answer from there. So it's kind of weird for me. But a trick that's usually helpful, especially like this, right? You have just 2 factors, right? That one and that one, is prime factorization. I would say prime factorization, at least in contest math, right, is something that comes up, extremely often, at least, relative to how much is taught in school, right? So let's try to find the prime factors of this because obviously these two have to both be factors. And so if we have a list of all the factors for this, maybe we can end up working it out, right? Maybe some trial and error, or whatever. So 1313, it looks like probably divisible by 13, right? Because you have this one here, which, like we know from our trick earlier, is 100 times 13, right? And then we have this right here, which is just 1 times 13. So it seems like if we add these, 101 times 13, that's 0. 101 times 13 equals 1313. So we know these are both factors, right? And if you want, you can envision this as the 13 replacing that one there, like that, and then 13 replacing this one there, like that, if this step was kind of confusing. But so we know the factors are 101 and 13. Now 13 is obviously prime. I think everyone can kind of figure that one out. 101, it's not as obvious, but on this problem you did get a calculator, and so you could, do not a small amount of dividing, but, guess and check and figure out 101 is actually also prime. So 13 and 101 are actually the only 2 factors of 13, 13, which means one of these has to be 101, one of these has to be 13. Now, obviously, we're dealing with all positive numbers here. Well, at least we can say that. I don't think it really matters. So we can make that assumption. So obviously, the y plus x is going to be bigger than the y minus x, right? So this one has to be 101, and this one has to be 13. Okay, so y plus x is 101, y minus x 13. So there's probably a variety of ways to figure this out, but basically, to find the actual values of y and x, right? If we have y plus x, let's say we're looking at like a number line, right? If we have y in the middle, if you add x, you're going this much this way, right? And then if you subtract x, you're going this much this way. So actually, y is right in the middle of y plus x and y minus x. So you can think of y as being the average of these two numbers, right? So if you want to find the average, right, 101 plus 13, 4, 1, 1, and then divide that by 2, divided by 2. That would be, looks like 5, 10, 1, 4, 7. So so the average of these two numbers is 57, which means y is 57. And then it's pretty simple from there. 57 minus x equals 13, right? You can do some algebra there. 57 minus x equals 13. Add x to both sides, subtract 13. 57 minus 13 equals x, and that is 4, 4. So now x is 44. So what was x again, right? Because it's not what we're looking for. We're looking for k. So what was this? Now this was, if we go back up to where we defined it, this was the square root of the number that you get when you put their ages together. And their original ages, right? Y is the square root of the number you get when you put their ages plus 13 together. So if we square this, then we should know the two ages, right? Because if we square this, we should get Kelly's age right next to Jack's age. So now 44 squared is, like I said, they give you a calculator for this because I actually, fun fact, do not know the square of 44 just off the top of my head, is 1936. So now if we go back to what we were originally saying x is, that means that this part is Kelly's age and this part is Jack's age. So now we have our answer as 19, but obviously we just did a whole bunch of stuff, so you probably want to double check this, right? So the first thing it said was that they're 17 years apart. So in theory, 19 plus 17 should equal 36. That's 16, 3. Okay, that part checks out. Also, you want to check, just to make sure you did that part right, the square root of 1936, because it said it should be a perfect square, right? And so if you go to your calculator, 1936, right, you get 44, what we just did. But also, it said if you add 13 years to each age, you should get another perfect square. So 19 plus 13 is 32, and then 36 plus 13, 49. Okay, so which means root 3249 should be an integer, right? Because that should be a perfect square. So let's see, 3249 in the calculator. This is 57, which means that we're good, right? Because we showed that their present ages, if you put them together, it gives you 4-digit number, which is a perfect square, right? Showed that by showing that this is an integer, and then we also showed if you add 13 years to each age, then you get another perfect square, right? And so they were looking for Kelly's age. So the number we got right, 1936. They're looking for Kelly's age to this part, so K equals 19. And that is the answer. So this one, I don't think it was too hard. Um, it was like a problem for like 3 people though, but we didn't really work together and we still got the right answer. But I think there were a couple tricky things here and there. I think 2 stand out in particular, as being particularly, clever tricks. One is the whole shifting it over thing by multiplying by 100. And that's a pretty common trick if you're ever looking at like, you know, numbers where you do something like this where you just put them together, right? You want to kind of make room for that other number by multiplying by a power of 10. Because if it was like 2 3-digit numbers, right? 1, 2, 3, and then 4, 5, 6, you'd want to multiply this one by 10 to the third, right? To move it over 3 times to make room, and then you could just add, right? So that was something that comes up not super often, but I do see it occasionally. And the other thing that comes up very often is prime factorization. I would say over here, right, we did prime factorization right here. I'd say prime factorization is one of the first things you should check for. If you get the sense that, oh, factors might be useful. I mean, obviously in this problem, it's probably not obvious that you're going to be factoring stuff until you get to around here, right? In the beginning of the problem, you probably wouldn't be thinking about prime factorization, but in general, if you think factoring something might help, things are being multiplied or something, then definitely prime factorization is something you should be on the look for. So yeah, that's this problem. Again, I think this was a relatively simple one, because this wasn't from the AMC like the other ones I was doing, but still a fun problem with a lot of insight connected to it. So let me know um, if you think my explanation sucked. What can I do better? If I did anything well, you can let me know, or just don't. You can suggest problems maybe. Um, of course, I'm not going to pick a problem if it's like way too hard or way too easy, I think, but I'm open to suggestions, corrections, whatever. So, or let me know if there's an easier way to do this problem. But yeah, thank you for watching and see you next weekend.